Welcome back, Pre-Calc Plus students. Today we're going to cover section 3.5 on exponential and logarithmic models. So the two models that we use a lot is exponential growth and decay. So for exponential growth, we have y is equal to ae to the bx. Y is always your end amount, okay, or end population, your remaining population. A is always the initial amount. That's what you're starting with. E is the number E. B is time. And X is our rate. Or actually, they could be in either order. Sometimes you see RT. Really doesn't matter what the letters are. But as long as you know this is initial amount, this is end amount, initial amount, rate, and time. Okay, or time and rate. For the decay model, the big difference, the only difference, is that the rate is a negative rate. Okay, so if you think about the graph of an exponential graph, the parent function for an exponential usually increases, right? When we take that graph and we reflect it over the y-axis, and that's what this negative does, it now becomes a decreasing function. So again, with that positive rate, we have an increasing model, okay, increasing exponentially. And then when the rate is negative, it's going to decrease. A population P of a city is given by P equal to 95,300, E raised to the 0.005t. So in this model, that 0.005, that's our rate. T represents time. 95,300, that's the initial population. And here they're saying that time t equal to 0 represents 1996. So this would be the population in 1996. We're asked, when did the population reach 150,000? So that would be our end population, which we'll plug in for P. So we have 150,000, and actually I can remove a couple zeros right off the bat. Save us a little bit of writing. So I'll change this to 1,500. It'd be the same as me dividing out by 100 if you want to think of it that way on both sides. Okay, so 953 e to the 0.005t. So to solve for t, I'm first I want to get this in exponential form. So I'm going to divide 1,500 by that 953. Oops, I didn't do that right. I put 2 zeros instead of 2 5s. Okay, so when we divide, we end up with 1.57397. And the thing I always try to do as I'm doing these problems is not clear my calculator. I like keeping those previous numbers in, and you'll see why as we go along and do these problems. Okay, so now I have my exponential form. Now I can switch this into log form. So I'm going to take the natural log, since it's base e. So the natural log of 1.57397, which again, I kept that number on my calculator, so I have all the digits. The natural log of that number is equal to my exponent. So now all I need to do is take the natural log, and I'm going to use my answer button on my calculator, and then I'm going to divide by this 0.055. So as you can see, I never had to clear my calculator, so my answer is going to be most accurate because I didn't clear out all those digits. And I end up with 8.247. So t equal to 8.247. So that means after 8 years, about 8.25 years. So if we add that on to 1996, that would happen in the year 2004. Okay, let's see what's next. Doubling time. Now, the time it takes for something to double, we're going to show you where that comes from. It's a nice, easy formula if you can remember it. But if you can't, this is how you can always come up with it. So we're going to start with our basic model, the y equals ae to the bx, or rt if you prefer to use that. So if something is going to double, no matter what I choose for a, y is always going to be twice that. Right? So let's say I said a is 5, then y is 10. Right? If I said a is 10, then y would be 20. It's always going to be that 2-to-1 ratio. So that's what we're going to use instead, is y equal to 2, and that would be a equal to 1. So I'm just going to ignore a. So I have my exponential form. I'm going to take the natural log of both sides, so the natural log of 2, or think of it as switching to log form, is equal to our exponent, which is b times x. Which again, if you want to think of that as rate times time, that's probably best for this formula. So if I'm looking for the rate required for something to double, then I would have to know the time, and I would divide by that time. So the natural log of 2 divided by t gives me the rate, which means the rate required for something to double. Whether if it's a population or if it's money, okay, it could be about lots of different things. But if you see a problem about the time required to double or the rate required to double, you want to think about this formula. This is the part you really want to remember, because if you're asked for the time, then you would need to know the rate, and you would divide natural log of 2 by r, and that would give you the time required to double. Okay, so we'll put an or in here. So it depends on what the question's asking for. You just divide by the other part. Half-life is a very similar concept. So again, we're using that model. Okay. Y is equal to a e to the, this time I'll just use RT. But this time, if it's half-life, half-life is the amount of time required for a substance to decrease by half. So that means our end result is a half. Whatever A starts with. So if we started with 100 grams of something, the end amount would be 50. So now it's a 2-to-1 ratio in the other direction. So when we divide, we would get a half. So now half is equal to e to the RT. So if I take the natural log of 1/2, or 0.5, that's equal to rate times time. So again, depending on what you're asked for, you would either need to know the rate or the time to divide and solve for the other part. Okay, so let's give this a try. So a certain population's growth rate is 2.7%. How long will it take the population to double? So again, we don't even know the population. We don't need to know. All we need to know is our formula, that the natural log of 2 is equal to RT. So the natural log of 2 in this case is 2.7%. Now remember, when it's a percent, we change that to a decimal by dividing by 100. So, oops, I left out my 2 there. So the natural log of 2 divided by our rate, which is 0.027, will give us the time. Excuse me. So I'm going to take the natural log of 2 and then divide by 0.027, and I end up with 25.67 years. Okay, so at this growth rate, that's how long it would take the population to double. And that's what that means, that each year the population is increasing by 2.7%. Okay, carbon-14 has a half-life of 5,715 years. So this is our T value. So we're asked to find the decay rate for part A. So if we start with our formula, since it's half-life, this would be the natural log of 1/2. Okay. And that is equal to RT. In this case, we know T. T is the 5,715 years times the rate. So I'm going to take the natural log of 1/2 and divide by those years on my calculator. And I end up with a rate of, it's very, very small. You're going to get scientific notation most likely on your calculator. So to this many digits should be enough, but again, try to not even round it. Okay, I'm going to leave that number right on my calculator because we're going to use that rate in part B to figure out the age of the Dead Sea Scrolls. So this says the Dead Sea Scrolls have lost 22.3% of their carbon-14. How old are they? So for part B, now this is a little tricky because remember, we're using our model. If they lost 22.3%, then we have to think about how much remains. Okay, remember, A is our beginning amount. Right? We start with 100%. If they lost 22.3%, then that means 77.7% remains. Okay, so be careful with the wording of these problems. If it said that that this was how much remained, then that's the amount you would use. But when it says that they've lost this amount, you have to subtract that percentage from 100 to get what remains, because Y is always, again, that end population or that end amount. Okay, so now let's see. We can also use our rate, okay, from part A. I didn't write that in here, but R is that decimal there. I'm going to divide out by the 100, so I have 0.777 is equal to e to the RT. I'm going to take the natural log of 0.77 and divide by our rate to get that time. So if I plug, and again, I'm not clearing that rate off of my calculator. I saved all those decimals beyond this too. I'm going to take the natural log of 0.777 and then divide, use my answer button, and I end up with, oh, actually, I believe this is the answer with the rounded rate, because now I'm seeing I'm getting 2,080 years. So it does make a difference whether if you round off or not. So that can be tricky too. Hopefully you'll have instructions on whether or not to round your rates off or not. But it can make a big difference. That's a 22-year difference anyway. Okay, so just to recap here, remember this is the formula you'll be using most of the time. Okay. For doubling time, try to remember this formula, and for half-life, Okay, if it's doubling time, it's natural log of 2. If it's half-life, it's natural log of 1/2. And then again, depending on which part you know, you divide by that part and solve for the other. Now, knowing this, what do you think you would do if it was the amount of time for something to triple or to quadruple? If you said take the natural log of 3, you're right. Okay, for tripling, that's the only difference. It would be natural log of 3 equals RT. Or to quadruple, it would be natural log of 4 equals rate times time. So you might come across a problem or two where they ask you about something tripling instead of doubling. So guys, I hope you enjoyed this lesson, and I hope to see you on Zoom before the year's out. If you have time, pop in and say hi. Have a good day.